So these are my Federal headphones for crystal radios and early radios. Not only are they not in phase, but the amplitude is way down on one of the elements. So the audio analyzer is already telling me more than I wanted to know about my favorite headphones. So what is the highest source of distortion in any audio system? That's a question that's been around for a while, but I think we can point at the system that changes the complete mode of the energy the most as being the place where the distortion can be the highest. And what we find is that transformers tend to be low distortion because they're converting electrical energy back to electrical energy. But transducers such as loudspeakers and headphones, they're converting electrical energy into motion, motion of the element that produces the sound waves that we hear. So there's a great opportunity for a high amount of distortion to occur with headphones. We found that the electret microphone was quite flat. An electrostatic device or a condenser mic, I think you find the same thing with some of these new electrostatic headphones. Certainly taking advantage with headphones today. We're going to find some really interesting shapes. You're not going to see these nice flat curves that you're used to seeing testing op amps and audio mixers and different equipment where you DC to daylight flat as a table, rolling stock as we like to call it, flatness. We're not going to be seeing that. We're going to be seeing some really flavorful curves with these headphones. Stand by for part 2. We're going to be measuring headphones with our audio test system head. So it isn't just about the headphones. I'm going to be struggling to use some very interesting audio analysis packages that you can find on the internet. These are often called audio analyzers or sound card oscilloscopes, that kind of thing. So I've picked out 3. There's probably 10 or 15 of them. I've picked out 3 of the popular ones, and we'll attempt to install those on the Windows XP machine that I'm using for testing, and we'll see which one works to allow us to do some simple measurements. And by simple measurements, I'm mostly interested in figuring out the drivers or the receivers, whatever you call them, if they're actually working and in phase, and if the drivers have approximately the same sensitivity each side, left and right. And then we're going to do a little bit of spectral analysis and look for some harmonic distortion. And finally, we'll do a frequency sweep and find out what the curve would be for the response of the headphones. If we can do some of that, I think this video will be worth watching. This is a pair of classic 1920s Federal headphones, and the Federal headphones have the large magnetic diaphragm style drivers. This headset is something I picked up at a ham fest, had no cord, so I just made a cord for it and randomly attached the 2 elements in series. So each of them is 1,000 ohms, so it's a 2,000 ohm headset. So works okay. I use it on crystal radios, but you never know what's going on with a headset like this. It's just, you're kind of in the dark. Now that we've hooked it up to the system, I'm putting in a 400 cycle tone, 400 hertz. You can plainly see that one of the drivers is more sensitive than the other. It's not radical. It's probably about 3 or 4 dB down. Might be noticeable, and that the 2 drivers are out of phase. So this is an example of something you could see on this test system. The next thing I'm going to do is reverse one of the elements wiring and see if we can get them in phase. Okay, that's better, but I can see another problem here. You can see that they're now in phase, but they're not perfectly in phase, which means that the windings or the magnetism on the two headphones is not identical. So this is a quality control issue. Perhaps one of the drivers was damaged at one point or got unmagnetized. These are the types of things you can find out when you're playing with old headphones. By the way, you can tell the polarity of headphones using a compass. It's an old trick. You put the compass on one side of the headphone, and then you put the compass on the other driver, and you can tell which end is positive and which is negative, or at least how to wire them together by using that compass. But you can see this is an imperfect headset. And we haven't even done a swept measurement yet. So before we get into the 3 software packages that I tried, I want to go over the basic types of headphone drivers or receivers. The first type, developed basically for wired telephony, was basically the single-ended armature type, which used voice coils wound around the poles of a permanent magnet, which were positioned close to a thin iron diaphragm. Both single and the more common double magnet types were produced. This became the most commonly produced type of radio headset from the turn of the century well into the 1940s for impedances between 100 and 4,000 ohms. These are your common 600 and 2,000 ohm headsets used in telephones and for vintage crystal radios and early valve radios. The audio current through the coils varied the magnetic field of the magnet, exerting a varying force on the diaphragm, causing it to vibrate, creating the sound waves. The requirement for high sensitivity meant that no damping was used, so the frequency response of the diaphragm had large peaks due to resonances, and it resulted in acceptable voice quality but very limited musicality. The moving iron driver is another type. In this design, the moving permanent magnet is attached directly to a plate of metal, celluloid, or a paper cone diaphragm. A large fixed coil would be wound around the outside, and this was an early way to drive more juice, more power in larger structures, such as in horns and paper cone loudspeakers. A balanced version of this type was also produced, but the balanced design was actually made to reduce distortion caused by the imbalance caused by the mechanical support structure. These supports are called reeds, R-E-E-D, and the reed was only on one side on the single magnet version. By incorporating a similar field winding at each end of the driver to push or pull it, a balanced reed support structure was produced. With this balance, you had much less distortion. Also around 1910, Nathaniel Baldwin developed a new idea that kept the magnet or magnetic field stationary and connected the armature windings directly to the diaphragm. To maintain high sensitivity and high impedance, the whole assembly became quite a bit larger than with the traditional fixed magnet types. The improved frequency response and sensitivity of the moving coil type was appreciated, but the cost and mass increase was not. Moving coil or dynamic drivers are still considered the standard of excellence in headphone drivers and loudspeakers. Planar magnetic headphones are in the same family as the dynamic type and produce sounds by regulating the electrical flow through a film that's been suspended between magnets with equal magnetic force. The magnets are placed on either sides of the electrically active diaphragm material. Upon application of current, the diaphragm gets electrically charged, creating a magnetic field, and when the magnets on either side of the diaphragm react with this magnetic field, it causes the diaphragm to move, therefore creating the sound waves that we hear. In planar drivers, instead of a coil going down the middle, there's a flat film that covers the entire diaphragm. Next, the biased condenser microphone was invented in 1916. This principle in reverse is the basis for the electrostatic headphone driver. Classic electrostatic drivers have an extremely thin membrane sandwiched between two electrified plates. With very little mass and suspended within an electrostatic field, this diaphragm moves with static attraction and repulsion to create the sound waves. The driver must be biased in order to keep the plate at a rest point slightly away from being attracted to the other plate. Without bias, the two plates would be attracted to each other and the whole thing would close. Electrostatic drivers avoid some of the distortions commonly created by other types. Standard dynamic drivers, which have diaphragms driven against the outside ring of the membrane, have inherent mechanical and resonance issues. The piezo effect was discovered by Jacques de Curie in 1880, and in 1933 the Aesthetic Corporation started marketing a crystal microphone. Doing this in reverse, the transducer acts like a driver element, so applying current to the outside of the crystal allows the driver element to vibrate, causing the sound. During the 1950s, a ferroelectric ceramic material, barium titanate, began to replace the Rochelle salt in transducers. Unlike Rochelle salts, barium titanate did not lose its piezoelectric characteristics when exposed to high heat or humidity. The low cost and high impedance of crystal earpieces allows this technology to survive, even if fidelity is somewhat limited. So this program I've been using, which is Sound Card Oscilloscope by Christian Zelins, I hope I'm saying his name right, is not actually freeware. He has a very reasonable price for a personal license for this software, and he also has a commercial license for the software. Headphones set up. Looks about right. Let's get them on there. Okay, the phones are on the head. So, what are the settings? For the signal generator, I'm putting in 500 millivolts, and I have a frequency of 400 hertz, as you can see here. And then the oscilloscope is set for 350 millivolts per division. We could do 0.5. So there's a half a volt per division. Now there is some wiggling around going on. You can see that. That's obviously I got some noise in there. And I do want to try a separate generator to see if we can get rid of that low frequency noise. But remember, the electrodes are extremely sensitive, so they're going to pick up anything. As soon as I'm tapping on the head, it's, so it's just as sensitive to low frequencies coming through the cord. So some of this is acoustic and some of it is low frequency rumble that's coming through from the computer sound card. Okay, I'm still not satisfied about that low frequency that's riding on there, but you can easily see now that I've flipped the phase on that one earphone that the two drivers are now in phase. So even with a not so perfect test system, we're at least being able to put the two drivers in phase. Also, you can see I've adjusted the line input, and the line input balance here so that the two are more equal, so I could study them a little more. When I put it back to the middle, you can again see that one driver is less sensitive than the other driver. So all I have done is set the head on top of a blanket that's located near the near the computer, and just isolating it from the computer case has certainly settled down the pattern quite a bit. Still picking some up through the air, but it's pretty attenuated. Okay, here's a pair of Beats headphones that were repaired apparently correctly, because the two elements are virtually identical and they are in phase. Of course, these are much lower impedance headphones than the headphones that we've been using, so I did have to adjust the volume control. So here's some low-end, mid-range type Maxell headphones, similar to the Beats. So here's the Maxell headset on our test measurement head, and we're looking at the frequency response, and you can see that it's fairly flat until you get up to the cursor position, which is 4.76 kilohertz. At 4.76 kilohertz, we do have a resonance point with these headsets. Okay, we're looking at the Beats headphones now, and let's see how this comes out. This is a log-log scale, so both the frequency response and the audio response are in dB, which makes it easier to see. There's no filtering in. It looks like the Beats has some resonance as well. A little higher in frequency. It says 5.48 kilohertz is where the resonance point is, but it's not quite as pronounced. There are some things going down in the passband that are happening, and that's my voice disturbing that area. So here's the consolidated R2s. And as you can see, this has really good pickup around 1 kilohertz. You can ignore my voice there, but you can see these are really set up for CW and for voice, and they fall off rapidly above about 2000 hertz, and these are communications quality headsets. I've got a low pass filter in of 200 hertz because we know these really don't work at very low frequencies, so I just filtered that out. Let's reset it again so my voice is not in the passband. So here are the World War II HS33 headphones that have the A and B receivers. As you can see, they're in phase, but not perfectly in phase. There's a slight lag between the two, and I suspect that has something to do with the inductance on the earpieces and how they've wired the set. I have not touched this wiring, but they sound okay. Again, military communications fidelity. So the military headsets, you can see as I'm talking, I'm bringing up the bottom, but military headsets pretty flat, and it has a peak, it looks like around 2.7 kilohertz, and then it begins to fall off. So I'm repeating the test we were doing on phase and amplitude at 1 kilohertz. As you can see, the HS33 A and B1 receivers are pretty much in phase at 1 kilohertz, so that lagging that we were seeing seems to have cleaned up at 1 kilohertz. So the headset is wired correctly from the factory. The sound card oscilloscope application also has the ability to measure total harmonic distortion. If you're measuring an amplifier, something like that. With headphones, it's less meaningful because most of this distortion is going to be introduced by the sound card itself. not as much by the microphone in the headset. As you'd see, it's reading between 0.2 and 0.27% total harmonic distortion. So this is the main carrier at 400 hertz. So you would see replicas of this if there was harmonic distortion. We're really not seeing anything. Here are the Nathaniel Baldwin headphones. My most sensitive headphones. I mean, these outperform everything that I've tested so far for sensitivity. And they are definitely wired completely out of phase. So I need to switch the polarity on one of the drivers. You guys probably did want me to test the AKG headphones. These are open format headphones. They're not the sealed type like all the others that we've tested. So audio will come out the back, and this is thought to give superior performance. Of course, you would expect them to be in phase and provide a very pretty picture, which they do. So let's see how they look in the swept mode. So we're playing with the AKG reference headphones, and we're going to look at what we can do with the sound card using the sound card oscilloscope program. So on this guy, basically you set the signal generator, and I've got it set for 0.5 volts, so 500 millivolts of drive. This drive is going directly into the headphones, so it's split between both channels. And on the scope, I've got him set up for 100 millivolts per division. Both sides look to be fairly equal, and it's picking up my voice. Remember, these are the totally open headsets, so they don't have a good seal. Audio goes in, audio goes out. So just remember that when you're using these style of headphones, you don't get the isolation of the outside world that you do with normal headphones. Now they call them reference headphones because they're meant to expose any abnormalities or any distortion. So some people find them very harsh and much prefer their less critical headphones. So anyway, we're not in distortion here. Everything is in the linear range, so it's important not to have the drive set too high. We can do a frequency response plot with some pretty good confidence right now. Now, to do a freq response, we should probably put in some filters. And I like to use a bandpass filter in this thing. And I'm going to use, I'm going to go 20 hertz to 20,000 hertz. Okay, that's my bandpass. And with the signal generator, we need to sweep it now. So instead of a steady single tone on channel 1 that we're sharing between the two elements, we're going to use a swept frequency, and we're going to sweep all the way to 20 kilohertz. So let's put in 20. And we're going to sweep that on channel 1. And let's start the sweep. Okay, it's now sweeping. You can hear it. Okay, let's see what's happening on the frequency graph. Okay, so we need to do something so we can see what's going on. Now the first thing we're going to do is we're going to go into the log scale. And we're also going to use the log scale for our amplitude. Then we're going to use peak hold so we can see what we're doing. So as you can see, these headphones are quite flat. They do have a peak. Let's investigate that. Looks like they have a peak right here. At 5.39 kilohertz, they have a peak. But that's not a bad resonance. So these headphones are not bad. Now if I was to change that bandpass to 10,000, and then hit peak hold again, okay, you can see how that bandpass filter has rolled us off at 10 kilohertz. So this is a second audio product by Václav Perouka, Czech Republic. I found it very easy to use. It's called the audio measurement system. Very quick to get up and running. It has a nice frequency response plot and quite a nice spectrum analyzer as well. This is another product I found on the internet that appears to just have a donation style licensing scheme. Let's see if we can get one more that can do the basic measurements we've been doing. So the first thing you do with this RightMark program is when you hit the run test, it's going to put you into this adjustment mode, and you're trying to get this level to be green. So you adjust your sliders on your volume control. In this case it's the volume control and the wave control until you get the drive into the green, and then it will allow you to start the test. And then you basically just give the thing a name like test 1. Okay. And it'll be listed here, and it'll give you the analysis of that test over here. And you get the response and the total harmonic distortion on the screen. And I'm just a novice at this. I've just started the program and gotten so I can actually run it. But this seems to be a really popular benchmarking program that people use to test their equipment. So it's a very popular program. So I can't say that we were 100% successful with this video. I did learn a lot about keeping microphones isolated. There was a lot of subsonic noise picked up by the system, and I learned a lot about sound cards, that's for sure. I hope you enjoyed this video on measuring audio headsets with a simple audio analyzer tool that you can download on the internet.